Good morning, everybody. Hope you've all had your coffee. I know I had my 2 or 3. So, welcome everyone. My name is Russ Fellows, and I'm going to be hosting this esteemed panel. So, Dr. Paul Burrell put this together and kindly handed it off to me so that he could be another great participant in this. So, have a lot of very high-level CTO people here, a lot of doctors on the stage. We're going to start on the far right with Al Fazio, who is a senior fellow in the Foundry Technology Development Group at Intel. Thank you. There we go. That's better. And Al, I'll let you introduce yourself in a minute. But so you've been instrumental in developing industry's commercial flash technology, multi-level cell memory, 3D crosspoint, and contributions include significantly shaping memory and storage landscape with over 30 patents. So anything you want to add to that, Al?
No, happy to be here.
Okay, great. Next up we have CJ. We'll go in order here. There we go, CJ Newbern. So CJ is from NVIDIA, distinguished engineer driving HPC strategy and technical I/O roadmap at NVIDIA for the GPU cloud, focused on pushing the envelope for storage and networking programming models at scale. CJ is a community builder with a passion for building ecosystems that extends the core capabilities of hardware and software platforms from HPC into AI, data science, and visualization. He tinkers with leveraging NVIDIA and vendor products in a lab packed with scaled compute, storage, and networking gear. So, CJ, welcome. Anything you want to add to that?
Sounds great. Thank you.
All right, perfect. Okay, next we have, we'll go back, there we go, Rita Wuhabi. Did I get the pronunciation slightly better? All right, great. So Rita is an influential figure in computing, currently driving AI strategies at Solidigm. With a background at Intel's CTO organization for network and edge, she has led groundbreaking projects in manufacturing, pharmaceuticals, and warehousing. Rita is passionate about democratizing AI and enhancing human capabilities through continuous learning and edge AI innovations. So her position allows her to work as a visionary leader in this field. Rita, welcome.
Yeah, thank you for having me.
All right. Next to last, we have, let's see if we can go in random order. There we go. Manoj Wedekar from Meta is a leading figure in Meta's technology division, focusing on advanced computing and solutions in AI integrations. His expertise in system architecture and data management has driven significant innovation in Meta's infrastructure, enhancing the performance and scalability of their computing systems. Manoj's forward-thinking approach and deep understanding of AI's impact on technology make him a key contributor to this panel. Thank you, Manoj. Anything to add?
No, glad to be here.
All right. Everybody's happy to be here. And last but not least, like I said, the organizer of this panel, Dr. Paul Burrell, also is a seasoned technology executive and entrepreneur with a distinguished multi-decade career. Paul was CTO of Veritas Software during the 9/11 emergency data recovery and co-founded the IEEE Hot Interconnect Symposium and SNIA. He has extensive experience in the design of fault-tolerant and disaster-resilient infrastructure designs at NASA, Sun Microsystems, Quantum, Veritas, and Apple. Paul's obsession with making transactions fast, reliable, and secure.
Thank you. It's a pleasure and an honor to be here amongst all of these technical experts in the industry. Thank you.
All right. So with that introduction in place, here, hopefully we have everybody up. There we go. All right. So we're going to talk about a few different areas, and I think probably one of the best high-level questions to start with is how do the needs of AI market differ from those of traditional HPC market regarding memory, storage, and interconnect technology? So maybe we'll start down at the end. Al, you want to start with that? Any thoughts on that question?
Well, I think in many regards, a lot of the AI stuff is kind of evolved from the traditional HPC supercomputer type of market, and a lot of the similar attributes of needing very high performance memory very closely coupled to the compute. And so in some respects, I think there's similarities. I think someone's phone is buzzing here. Someone left their phone. And so I think there's a fair amount of similarity in that regard. And I think the thing that's kind of different now is really the scale that's taking place. And in particular, if you think about between memory and the compute, what really is interesting to me about this is that in a memory cell, it probably takes a couple of pico or a fraction of a picojoule per bit to read and write, once you get through the circuitry and things like that. You move it a few millimeters and you spent more energy moving that bit just a few millimeters, a handful, less than 5 millimeters, than you did reading and writing with all the circuitry that's around that. And so in AI right now, the real issue is it's all about memory bandwidth and close coupling with that compute, but how do you get the capacity that you need at that bandwidth? So it's a capacity density, a compute density, and if you're doing it at scale, you're burning a tremendous amount of power just moving that data around. And so it becomes a very interesting kind of multi-dimensional problem. Many of the similar things that took place, I think, in traditional supercompute and HPC, but just I think it's on steroids now.
Right. So Manoj, maybe you have a slightly different perspective, being more software focused. I'm assuming working at Meta. Any thoughts on that the differences in
not the differences.
HPC?
I think I'll put it really well. I mean, definitely there is a strong roots from HPC, and that has evolved the AI. Maybe I can add a little bit of a different twist to this from the infrastructure perspective, that for hyperscalers, it's not how AI is different than HPC, but also how AI is different from our remaining general purpose compute infrastructure, because that's where how we build the data centers, how we build our software, how we manage that whole infrastructure is fundamentally different for the whole AI space. Primarily because most of the general purpose compute infrastructure runs with an expectation of failures. You have millions and millions of small stateless tasks that you can make sure that some of them just fail. We have the availability in the software infrastructure to allow for that. So the hardware can be relatively acceptable to be failing. We can manage it. The software is aware of it, and software can deal with it. The AI space, though, the software is not the same way. You have a task that runs across lots of compute units, which are the GPUs, and any failures in that job, failure in the part of that job can lead to the whole job failing, which may be running for weeks and months. So the reliability expectations and the availability expectations for the AI infrastructure are dramatically different. So, but having said that, of course, the memory challenge and all other challenges remain same for the system composition. But to run the whole infrastructure, there's a fundamentally different expectation from the whole infrastructure, and also going up to the component level, the memories, the connectivities, the networks, the cables. There's a significantly increased awareness of how the failures happen and how to deal with it. So that, I would say, is some specifically different ones, I would say.
Okay.
I hear two answers to this question across the industry. One of them is that HPC and infrastructures for AI are somehow going to merge together sometime in the future. And the other is that they're going to adapt differently and have different tiers of networks that have to be accessing them. The north-south network will be relatively consistent with what we're doing today with clone networks, but there are other things that can replace them, are like direct networks that's used in at the very top, where you can get direct access, perhaps through a MEMS device, from one node to another without any of the intervening switching delays. So I see this evolution going in several directions. Very interestingly, I'm looking forward to seeing a lot more innovation in this area instead of stagnation on old architectures.
Right. So Reed, do you want to pick up on that, or I have a slightly different question, but if you want to pipe in on that, that'd be great.
I want to augment or a little disagree with the previous commenters. I think these days when we talk about AI and we stop there, it's almost like we're saying computer science. The field is so large, and the answers assumed just training and data center. And I want to remind us that a lot of the AI innovation is starting to happen at the edge. And that is going to look very different than HPC. As a matter of fact, I keep telling a lot of my colleagues these days and the customers that we spent as a community the last several decades moving data to where compute is. And now we're realizing that data is even more valuable than compute. So the edge really is bringing back all of that innovation in new ways where things are going to be distributed, data is going to be distributed. And it's no longer where training happens once and inference happens forever, right? We're seeing a huge continuum of things between training and inference, whether it's continuous learning, whether it's tuning of LLMs. So really comparing it to HPC is, I think, very restricted to only some of the training that's happening at large scale.
Right.
But think about all the interesting things that are going to happen in factories, in hospital rooms, on the road with autonomous driving, and it looks nothing like HPC. It's actually a new way of compute that is so ripe for innovation.
Okay, great. CJ.
So I think you could say that rather than AI replacing HPC, it's actually building on HPC. So HPC, a definition of Thomas Schultes is kind of a godfather of HPC, is that's about scaling up and scaling out with rigor and discipline. But I think if you see some of what's changed and what's different, in HPC, typically the way you scale is that you're using weak scaling. So you do the same thing on bigger and bigger machines in the relatively homogeneous way. I think what we're seeing here is that we're going after strong scaling, which is why we need a radically different kind of interconnect, something like NVLink, to be able to have lots and lots of compute resources work on the same part of the problem and solve that as quickly as possible. And that radically changes your architecture. That's why you need a GPU that's the size of a rack. And it also shifts, to your point, working at the edge as an example, but even inside a data center, you're going to need different kinds of storage technologies for different purposes, where you're ingressing your data, you're pre-processing your data, you're doing training and inference in different parts, and each of those demands a different kind of technology, including in storage, and hopefully we'll get to more talk about that differentiation.
Yeah, definitely have some questions on that. On a slightly different topic, so looking at energy efficiency, Paul Burrell, I'll start with you. What possibilities exist to improve energy efficiency in AI and storage systems?
So I've talked to a lot of people and changed my opinion actually just in the last couple of days because there's a lot of discussion, especially with some of our colleagues here in the audience here, about what the cost is. It's reaching a point where the cost of moving bits is a lot more expensive in energy than the cost of computing bits. That's a big deal. And so I'm thinking back, what innovations have we seen in the past that we could look at? Like, for example, we used to defragment disks, in our file systems. Don't do that anymore. But what's happening now is, could we think in terms of defragmenting the whole data center? Or even, when there was this, VMware came out with this idea of vMotion, which allowed you to move a virtual machine and then continue to address it and have everything continue to work with a very fast failover. And that can only work at layer 2. You can't do that layer 3, unfortunately, which is why it doesn't work for containers. But that brings into mind the idea of if you can condense a lot of virtual machines onto fewer machines so you can power down the machines you're not using, that's one way of reducing power dissipation. But another one might be a more generic form of, let me call it, power gerrymandering.
Okay. Yeah. So CJ, any thoughts on power efficiency in general?
I think power, we have a lot of people who are coming and joining this fray and want to be able to either use the systems that we give them or to develop new applications, but they don't know how to deal with power. They don't really know how to deal with performance. So essentially introducing layers of abstraction beneath which you can do innovation, I think, end up being really important. So I totally agree with what you were saying, Paul and Al, about sort of the movement of the cost of moving bits. That kind of problem is beyond most users' capacity. So being able to, we're introducing some things that take kind of a serverless approach where as an application trying to get some work done, you don't particularly care where the data is, how it's formatted, or how close it is, or what it's called. you're just operating on the data, and you can relegate to a runtime system, and people that are really good at tuning performance, tuning energy efficiency, can manage data orchestration in the background. And that there's a lot of room for sort of democratizing that and having lots of people innovate and decoupling that from the people that are trying to specify what should be done. And again, I think that being able to, this is a tremendous growth area for being able to get smarter about how do we sort of pre-partition the data and predict what's going to be most effective with that. And I think AI probably has a part to play in that that's yet to be discovered.
Okay, so using AI for AI, yeah. I've heard that a lot. I'm waiting for that to happen. I'm sure it exists. So Rita, any thoughts on energy efficiency and
yeah,
techniques?
actually, CJ brought up a good point about, it's very easy for the developer these days to spin up a task or a job, right? We made these abstractions, and it's fairly common for a grad student or an intern to spin up some compute somewhere, and it's consuming power. As a matter of fact, how many of you heard a story or experienced it yourselves where you spun up compute in the cloud and forgot it there, and it ran for days, and then you got slammed with a bill?
Yeah,
it's painful. But imagine that your compute that you forgot about it has been running, has been consuming power. It's moving the bits, but it also, these abstractions and abstracted layers that we have created for my 13-year-old to be able to spin up a Hugging Face model and do whatever he wants cost money and power and resources. And honestly, a lot of people, it's kind of, I hate to use the word, but it's a little bit of a sloppy use of the technology. So we have to figure out how to be more efficient. I think AI is maturing and has become the killer app, that it also has to become more efficient in power and moving bits. Everything that everyone have talked about, I fully agree with. And it's about, wake up call these days when everybody's seeing the bill, whether it's the power bill or the compute bill, to figure out how to be more efficient in our use.
So the Wahhabi household is pretty strict, I'm guessing, so the 13-year-old has to start spinning up Hugging Face models. Holy crap, man.
It's a little scary, honestly.
Okay, start them young. All right, Manoj, any thoughts on energy efficiency? I'm sure with, 10,000 GPUs, I'm sure that's of no concern to Meta.
Oh, no, not at all easy. But I think I wanted to bring back to that point of the discussion, actually, the efficiency, and talk about L that brought up the point of cost of moving the bits, which is what is changing a lot. If you think of taking the 10,000 or 100,000 GPU clusters, the amount of power and amount of cooling that is required to cool the whole thing is the important aspect. And as we talked about, the moving the bits, as you make the scale-up cluster or a scale-out cluster, the moving the bits is the most expensive. This is why we see that actually the innovation is happening is to keep on bringing things closer and closer together. This is where you begin the whole systems coming onto the wafers or all in the die and coming much closer with the chiplet kind of technology is going to become more and more prevalent, because you want to bring the bits in closer. If you have a memory requirement, the memory bandwidth requirements for GPUs are easily in the tens of terabytes per second and growing, which if you start moving them out, the cost is very high from the power perspective. So you need to start bringing them together. That requires a technology, that requires manufacturing technology to get more die-to-die functionality working at a higher bandwidth. Your shoreline matching and the capacity and the functionality coming from different vendors at the different memory technology points. So I think a lot of innovation is going to continue to come in this area in coming years, that will drive the energy efficiency by bringing things tighter and tighter together. The amount of transistors we can put per square millimeter is not growing fast, but how many things we can combine together is where the innovations will continue to happen.
Okay. So Al, you wanted to jump in?
Yeah, I think this is a really interesting multi-dimensional problem. You think about it from just the physics perspective of you not wanting to move things over a large distance because you'll just be spending the displacement energy in moving wires around. But then you have a software problem because as you bring those bits in to a smaller location, you have a finite amount of capacity that you can act on. And so how do you partition the problem down to a small enough compute? This is one of the reasons that compute and memory or processing memory really has never taken off. The compute that I have there doesn't have the data, so I need to have it over there. And so it's a hard problem. This is not one of those easy problems to solve, because it's how do you get things physically closer to the packing of that, the bandwidth issues
Right.
in there, along with, is it a large enough cluster that I can do meaningful work
Yeah.
on that cluster, which is a large software problem in there. And to be honest, that if you're working on something as like an embedded system, you'll work on trying to figure out every cycle. Those of us old enough have coded in machine language or assembly language. You look at every cycle, but there's only handfuls of people that do that. If you really want a developer community, you need layers of abstraction, and those layers of abstraction actually add layers of inefficiency to that moving of data around. So it's a hard problem both to solve technically, but then how do you scale it out to a large development community?
And find the right kind of parallelism to use on your accelerator.
Exactly.
Right.
If I may just follow.
Sure.
I think Al brings up a very good point. And this is precisely why the whole problem for energy efficiency for AI clusters is completely hardware software co-design. There's no more independently developing hardware and let software work on it. It's really the overall optimization, the memory part of it. Actually, you will have the bandwidth optimized functionality staying closer to the processing units, but then you'll have capacity moves a little bit farther. But software needs to be very much aware of what goes where, if it has to optimize the problem.
Right. So on a related note, so talking about persistent memory technology and comparing that to traditional storage and even traditional memory, and what advancements might we expect to have in that? So maybe I'll start with you, Rita.
Well, I have a position that we have to think outside the confines of the von Neumann architecture. And I think bringing compute and data as close together as possible is the way for scaling AI. And both, with a co-design with software, power efficiency, understanding how do we deploy at large scale. But if you think about it, this revolution actually has been ongoing for a while. I would argue that it started with the smart NIC, when the networking community said, I can no longer route things efficiently by always going through a central point. I have to move some of the intelligence to the network. Right. And I think the same is going to happen where we have to move the intelligence very, very close to where the data is. Because by the way, we have made it so easy for people to collect a lot of data. And now all of us are swimming or sinking, depending how you look at it, in data, and not all the data is useful. No. So we really have to start at every stage looking at the data and being able to process it along the way and understand how to route it intelligently. And that has to become very distributed in order to scale.
So Al, I think this is probably a question that's near and dear to your heart. Any thoughts on persistent memory technology and comparisons to storage and memory?
There's a lot of scars. We were talking a little bit of, just in the hallway ahead of this. I find persistent memory is near and dear to me, having done 3D Crosspoint. I think the challenge in a lot of these things, as we were discussing, is how do you introduce something very revolutionary in a system? We knew about persistent memory in the 1950s with core memory, and then we kind of forgot it. And so a lot of the software infrastructure doesn't understand it. A lot of the storage industry doesn't really understand it. When we were trying to first work on kind of how do you come up with a very memory kind of like storage, well, the storage kind of software infrastructure believes that, hey, it's going to be microseconds and I need multiple replications of that software, and geez, I actually have availability centers that have to be 100 kilometers separated for disaster, and now I'm limited by the speed of light in there. And so there's a whole infrastructure that has to change in there. And so it's a little bit easy actually to come up with the solutions, but then how do you build out that whole infrastructure that has to evolve around it? Right. And so I that was my lesson learned. It's really it's less about the individual technology than it is how do you bring along all the pieces associated with that. Particularly, someone says, well, I already have all my software built in this data center. I can't turn that.
Right.
And so I think those are the things we have to think about is for any one of these is, what are the tipping points that allow a lot of these other technologies that have to come along in order to enable some of these fundamentals.
Yeah, the hardware is only as good as the software that enables its use, right? I mean, it's more than just a device driver, it's the APIs. I know SNIA did some work around that, partially worked on by Intel. Andy Rudolph, I don't know if you know him.
Worked with him very closely.
Andy Rudolph hired me into my first job, and I still remember the interview questions he gave me. But anyway, so he did a lot of work on it, but that can't happen overnight, and it's still ongoing and probably more work to be done. So CJ, any thoughts on the hardware or the software aspects of persistent memory?
One of my last talks I think I remember giving before I left Intel 8 years ago, they needed somebody to talk about PMEM, so I jumped in and talked about that. And what struck me at the time, and still strikes me, is some of what you're getting at is, as technologists, we not only have to invent new technology, but figure out who's going to use this and how much do they need to change how they're thinking. And I think people aren't used to thinking of memory as being persistent. It's a little bit of a leap. However, I think there's a flip side way of looking at that is instead of changing people's thinking of using what's available, hey, persistent memory, disk storage, as an extension of memory, and being able to say, what I really care about as a user is data. And if I have huge quantities of data, then I want to ask, where do I put that? And one of the most effective place to put that from the total cost of ownership perspective is to actually use NVMe. So this is one of the things that we're seeing with this new classes of applications that need more data than can possibly fit in memory, is extending and spilling that over into disk. There are times when you need to do that in a persistent way. You may need to draw in data that came from something else as a different phase, and you've used storage as an intermediate phase to transmit from one stage of a big pipeline to another. And persistent storage has a great role to play in that. Or you may need to archive something, and those don't really fundamentally demand that people come up with a radically different way of thinking about data.
Right. Paul, any thoughts on the use of persistent memory?
As the speakers are describing how they see things, I see a lot of agreement in how this is going to happen, but maybe I can describe it as there's multiple waves happening in change right now, where maybe all of us have a chance to see one or two major paradigm shifts in our lifetime, but when all of the planets are aligned, you can see there's something big going to happen soon. And the three things I see are the miniaturization of packaging because of chiplets, and how the economics of that changes the story. I see the way that AI in particular is changing the access patterns, and the fact that we need to access things as graphs much more than linear memory or linear access in storage. And the third being the innovations in networking, which are possible. And we see lots of things. Even Ethernet is being reinvented these days. And of course, we've learned a great deal from InfiniBand and from NVLink. So I see these three separate waves as all happening at once. It's like there's a tidal wave about to happen where the innovation can really start to come in.
Yeah.
I
I just going to continue the thought that Paul started is, I think the innovation is going to be really rapid. Demand, at least, is very rapid. I think the challenge that industry will need to go through is basically the difference that in the past has been extremely open innovation. The technologies like Ethernet or TCP or memory technologies, anything has been very open because they need to interoperate in the systems at different level. I think the demand for performance and demand for speed for that performance is so high that there is a risk of everything getting more and more closer and tighter and hence more proprietary. So I'm just looking at that as a potential warning for us to see how the innovation can go fast.
Right. So this was my question, which is essentially that the current state of the art with transformer technology and a little bit diffusion technology and AI is that as the problem size doubles, the mathematical complexity grows exponentially by a factor of 2, right? So in order to increase the problem space that's addressable, do you put more of the impetus on hardware, just scaling up and figuring out ways to grow the hardware exponentially, or do you think there should be more focus on software to make, come up with technologies that are hopefully big O of n squared more efficient, right? So any thoughts on that? I'll start with you, CJ.
Yeah, it's really clear there are on the order of 5 different kinds of parallelism that you really need to exploit in order on a scaled system. So we're in the process of bringing up systems that are Grace Blackwell systems where you can get 72 GPUs in a cabinet, and then you can lash those together with InfiniBand or something to create something with hundreds of or tens of thousands of GPUs. And it's really clear that I'm working with a lot of the guys that are essentially carefully crafting, looking at what are the different kinds of parallelisms available and to what degree, and for each of sort of the instance of the parallelism, what are the communication patterns, how communication intensive is that, and how do I map that onto the underlying system that I have? And that goes back to this earlier comment about being able to use strong scaling wherever you can and maximizing the bandwidth that you can get and minimizing the latency and being able to sort of reduce, you talked about the abstraction, reduce the overhead by just being able to do direct loads and stores to those. So it's very much, I wanted to reach out and say, let's do co-design together. Because working both sides of those problems of seeing what it is we need to do in the hardware and the software is critical to success. And we as a company, are supposedly, you might think of us as a hardware company, but we're very, very, very much a software company. Of the only way that you can make use of all of that hardware is through a tremendous amount of innovation all the way up and down the stack to make that successful. So it's a big barrier to entry.
Right.
So
Rita,
yeah, I want to add to this. So I'm in agreement with what you said, but what I don't like is the fact that when you started, you said, hey, when I double my problem, when I double my data,
right,
the complexity is going to go exponential. And I think we should stop, and we're seeing academia, by the way, innovate big time in this space. We should stop just feeding the data blindly. I have numerous examples of customers, especially in manufacturing that I worked with, where they put a camera on the factory floor, and then next thing you know, they have 30,000 images, they have few terabyte worth of data, and now they have to go and annotate them. And no control engineer is going to do that. So what we need to look at these images and say, well, 80% of them are of partial products and really boring conveyor belt images that no one cares about. We have to identify those and dump them and not show them to the user, because we reduce the cognitive load, we reduce the training time, we have a model that converges much, much quicker, and we have an inference that runs much, much faster. So it also, we have to do the smart things along the entire pipeline. And I don't think just continuing, unless you're doing LLMs, right? Continuing to just feed data is always the answer.
Right. So apply a little human intelligence into the process as well.
Well, no, it doesn't have to be human, right? Because
right,
AI today is doing things like selective annotation, where you figure out through AI, you cluster your images, you group them, you're like, these 5 are the most representative. Let me start with those instead of showing the 50,000 and have them be overwhelmed.
Right. Yeah, Manoj, any thoughts on the
No,
hardware-software
I really
breakdown?
like the point Rita made, so I was just thinking about that. I wanted to, but my thought process was also on the continuation of what CJ was thinking. The hardware-software code also goes on to multiple axes, right? In the sense, there is a limit to how many transistors I'm able to put every time I have a manufacturing process improve. Maybe I'll get 15% or 23% or something around that every time I go, which basically means the remaining has to come from some software level optimizations. You go from different level, you go from FP32 to 16 to 8 to 4. So definitely your performance is growing, but you're trading off something. You're trading off accuracies. You're trading off things that are acceptable at an overall solution level. networking perspective, the software needs to be aware of where the networking is. As you just said, and you have a scale-up network, you have a scale-out network, but you're going to decide which part of the parallelism is going to work, on your scale-up network, which part is going on a scale-out network. So we are coming to a level where hardware will continue to grow and enable memory. We talked about what stays in tier 1, what stays onto tier 2. That is again more of a hardware and software decision. So I think the gains that we're going to continue to see going forward are going to be something that hardware and software are going to go together, at least in the AI space that I'm focusing right now. Right.
Can I quick share an illustrative anecdote for that, just
Sure.
to make that point? One of the things that I mentioned that we're in the process of optimizing for this next generation system, a fun game that's being played is we have some folks that designed a simulation environment, DL Sim. You can guess what the DL might stand for. And we're noticing, hey, there's a discrepancy between DL Sim and what we actually measure with the software stack on hardware. And the nature of many of the discrepancies are actually the people that designed DL Sim made very optimistic and aggressive assumptions about software being able to operate at speed of light and do really the best. And so the problem of sort of approaching the software and the simulator together isn't, oh, the simulator's broken, let's make the simulator more accurate. It's actually the software's broken and it isn't optimized enough. We're finding pain points that we're stumbling across that are hurting us. Let's go fix the software to be more like those idealistic assumptions. I thought that was fun.
So Paul, any thoughts on the breakdown between hardware and software optimizations and where the focus should be?
The conversation was wonderful, and what it made me think of is that we need to shift from like statically configured linear processing to statically configured array processing to perhaps dynamically configured graph processing.
Okay. So Al, any thoughts on the hardware, software?
Yeah, I think going back to your original question about the exponential growth and the complexity, right? With the data, I think there's two parts, and I enjoyed the metadata on the meta paper on recently on Llama, which I think did a good job of illustrating the point you were making, CJ, of what amount of how do you do the parallelization for what type of communication bandwidth I need. I think that was a nicely written paper to kind of do that. And I think there's going to be more of that, which I would put on the evolutionary side. But one of the things I think from a basic academia that I think is missing is you look at all these various things of algorithms, and everyone comes up with the next algorithm, and you really have a hard time to test, okay, is this at a limit? Where is it? And I started thinking, well, why isn't there like a Shannon limit associated with machine learning or AI, similar to how there is on communication channels? Turns out, I did a little bit of research. Actually, Shannon, right after a year after his famous paper, wrote something on the entropy of language. And so I really think there's almost something that people have to go back to in academia, which is more of those fundamentals. And is there a very different way to approach it from a fundamental perspective? I do agree in the near term, people are going to be doing the different levels of parallelization, map that to networks, map that to communication patterns. But if you really want to solve the problem, I think we got to kind of deal with it a little bit differently in the basic academia.
Right. So change gears a little bit, and instead of talking about the scaling of compute and memory, let's look at the networking a little bit more. So you've been involved with Ethernet, and so broadening that out a little bit, generally you're going to ask, are the existing networking technologies, InfiniBand, Ethernet, maybe NVLink, sort of, sufficient, or can those continue as evolutions, or does there need to be a revolution in the networking technologies?
So I spoke to Bob Metcalf recently, and he gave me some fantastic anecdotes. He said, what we do is we find the best networking technology we can every year, and we call it Ethernet. and it turns out, the other thing he told me was also very funny. He said that because of all the opposition to Ethernet originally, a lot of it from big, large, established companies, they came up with this idea that Ethernet doesn't work in theory. It only works in practice. so to Al's point about we have to go back to Shannon to understand what we mean by the theory here.
Right. All right. So CJ, any thoughts on the networking from your perspective?
So we are doing, as you might imagine, it was a big step for us to acquire another company for some change of $7 billion to go hook things together, and that's kind of exploded since then. And we've just recently been talking about a number of innovations of trying to address some of the shortcomings of Ethernet with respect to congestion control and being able to support multi-tenancy. There are more things coming with that, I think, that are yet to be revealed and that you'll be hearing about in a while. I think it's also one of the interesting developments that have been, for example, that happened here first in InfiniBand has been able to put compute in the network. So we have something called Sharp where, particularly for the all-reduce thing, and like nobody really seems to care very much about all-reduce, but altogether we put something in there for it that can essentially do compute in the network so that you can do a reduction in the switches rather than having to move all the data to the endpoints. And this gets to your point about sort of how do you make things more efficient in terms of moving data by figuring out where does data have to move and what are the communication patterns and how can we accelerate that?
Sounds like graph theory. I don't know. So, Al, any thoughts on the networking technologies and evolution versus revolution that needs to happen?
I think there's on two fronts. I agree that distributed computing through the network of how you're processing things is going to have value that's in there. I also think there's interesting aspects. Again, we're talking a little bit earlier about is optics having a resurgence, and again, if you're trying to solve a problem over a football field size data center, just cabling of wires and all the aspects of that are going to be a problem, and does allow you to do some sort of whether it's optical computing or optical switching, or how do you bring optics in to solve some of those problems, I think are going to put new twist that's on there. But there's another part which is about the network, which is as soon as you get into the network, you're getting into software protocol. And as soon as you're getting into software protocol, you're no longer treating anything like memory, right? Because it's just too slow.
Right.
And so
And not reliable.
yeah, and so how do you think about that? How do you not put those layers on that? And so I think those are kind of I don't have a quick answer for any of that, but I think those are the problems that need the focus.
Put it in the FPGA. In the SmartNIC.
Did I miss anybody, CJ? Or Manoj did?
On the network side,
Yeah.
I was just thinking about actually since there are networks have separated out your scalar front end, and Ethernet has been in all the places except, as you said, the memory network side still seems to be now separating it out especially on the scale-up side. And I think Paul brought up a good point that Ethernet ends up basically adopting anything that is required, but it doesn't have the memory semantic. And maybe CJ, perhaps you have thought actually looking at, because both of you guys have both of those fabrics. You have Ethernet fabric and also you have this memory fabric, which is NVLink. I don't know whether Ethernet is going to get there. There are efforts in that area. Whether the scale-up can run on the Ethernet. This is an area I think we'll have to see, because the networks tend to, as Al was saying, you have this whole reliability to handle. That's why typically Ethernet has TCP and RDMA and everything that you do. Question is basically, can compute deal with that scale-up kind of expectation of closest access to the memory, or does it continue to require specialized fabrics as we have today? So we'll have to see that.
Right. So I'm going to combine a couple questions here. So in terms of adoption, there's a lot of interest, a lot of money being thrown at AI right now by companies not wanting to be left behind. But that's not going to last forever, right? So companies are throwing money at it right now, not wanting to be left behind. But relatively short order, they're going to want to see some returns, right? That's one issue, is how do we get from the land of theory and a little bit of practice in HPC environments to practical business outcomes for Fortune 2000, and combine that with better power efficiencies, which aren't as big of an issue in the US, but I know in Europe, any of you who've traveled to Europe or have European customers that you talk with, we've heard from some of our European clients that not only are their data centers not able to grow power, they're being told they have to reduce their power consumption. So faced with a possible reduction of power and the need to get AI into production and producing something with business returns, what needs to happen in the next couple of years to make those things happen? Who wants to? I'll let you start with that, Al.
Well, I think when we think about AI today and fear of missing out or anything like, most of the things going in AI right now are about training. But for AI to really be pervasive, it's not going to be in training. It's really going to be in inferencing, which is because you think about my CEO uses this analogy. How many of you develop a weather model? Okay.
One.
How many of you use a weather model? Right? And so it's really about the inferencing and things like that. And if you look at the workload, it's a very, very different workload. You look at the arithmetic intensity of a training workload versus the arithmetic intensity of a inferencing workload, particularly with transformers, which are all in the decoder, so it's all just vector matrix multiply, arithmetic intensity of 2, right? It's a different problem. You probably need to a different way to go solve that, which is going to lead to a different performance, energy efficiency dollars going after that. And so I think it's it's not like all of a sudden I'm going to throw away my transistors and my package and my memory. It's just how are you using it? How are you configuring it? What are you? How are you optimizing for where those problems will lie, so that you can make money on it without spending $1 gazillion on power.
Yeah. So Manoj, any thoughts on helping to further democratize, although Meta's done a great job.
Yeah.
Thank you for Llama 3, 3.1.
I think Al said it's correct. I think we are in the early phase of AI. So if I look at from hyperscaler infrastructure perspective, for the general purpose computing infrastructure that we have had it for many years now. So we are used to defining the systems. We are measuring the system, measuring the applications, and make sure that the platforms are optimized to be not only the cost optimized, but the power optimized, because power is where our most of the challenges tend to be. The AI is in early phase. If I just look at the spider chart of different applications and what components they use to what level, it's completely out of shape because we don't know yet. They are changing all the time. They are still in the early phase. So we continue to make sure that we try to get optimization, but today it is mostly still investment. And so you try to optimize to some level, saying that, hey, try to keep on bringing memories closer together. That way actually picojoules per millimeter is going to be much more manageable. So there are at hardware level optimizations today happening, try to bring it inside the rack. As we talked about, give lots of GPUs in a single rack, try to optimize it there. But I think the long-term solution is going to be actually making sure that the SKUs that are defined are optimally designed. Today, when we have very memory-oriented workload, we tend to put tons of GPUs because that's where my memory is, and I may underutilize GPU. Right. So as we see in the future, we have to make sure that we will understand our use cases for training and inferences better, and we'll optimize it for power.
Right. So Rita, any thoughts on this? Although it sounds a little bit like your thoughts on the edge as well.
Yeah. So before coming to Solidigm, I spent 8 years at Intel, and I worked with a lot of what Intel called end users, so factories and hospitals and so on, to bring AI. And almost every time I visited one of those customers, we started with an ROI discussion, return on investment. And one of the customers actually went public about the engagement, so I can mention them. We did a big project with Audi manufacturing, and I went and visited them in Germany, and we spent 3 days walking through use cases. And there were so many use cases that as a data scientist, I was salivating. Oh, this sounds so cool. But we don't usually in businesses do something only because it sounds cool. So you're right in the sense that today we're doing a lot of things in AI, training very large models because it is cool and because we're trying to advance the technology. But at some point, all of those decisions are going to go back to ROI. We're going to find those use cases where it makes sense, but hopefully with democratizing using models and using a lot of innovation and awesome hardware, we'll get to a point where more and more use cases will be affordable. And we'll be able to solve some stuff that has been sitting for decades, people thinking, oh, I'm never going to be able to solve this. So we have to get to that discussion, and power is one of the equation. Power, hardware, scaling, human acceptance, and so on, and obviously business relevance.
Right. So Paul, your thoughts on this?
Oh, I have many thoughts. But the thought that comes to mind is when I did my transition from being a pure nerd as a distinguished engineer hired by Sun Microsystems, and they gave me this job of managing the new product introduction process. And they said they needed more, they needed to switch to birth control instead of euthanasia for projects. I took that on as a challenge, and I got some professional help, and you'll hear me on the web being quoted. There's only one thing worse than an engineer who's never been to see a customer, and that's an engineer who's been to see just one.
Yeah, that's a good one. CJ?
So I think gone are the days when we had time to adjust to new tech. Things have come onto this treadmill where there's this self-fulfilling prophecy where every 2 years the software models and the usage models and so on are just radically changing, and it's unsettling. And I don't know how many of us are having AI write our presentations for us or do our engineering work for us, but many of us are lagging behind that. But I think that there's some adjustment required. In a recent discussion Jensen had with Mark Zuckerberg, he talked about everybody can have a couple personal models that can sort of figure stuff out for them or do whatever it is that they need to do for them. And that's a pretty new world. And that's, going back to the enabling discussion we were having, I don't know what that enabling is, because it's really reaching the whole world and our personal habits. So I think that'll take us a while to catch up to. But doing our investment is basically in doing a vertical integration of trying to understand some of the particular problems that people are working on. And one of them, Rita will be talking about at Supercomputing, is some work we're doing with sort of AI at the edge of integrating, because so much data is coming in so fast. How do you figure out what's interesting about it, and how do you note, back to your conveyor belt example, how do you have a model of what you would expect so that you could notice something that's different? Right. I heard a story about somebody who came from Japan to Oak Ridge National Labs, and they set up this experiment looking at microscopic features in silicon and looking at some processes under temperature and pressure. And they got all the results, and they went away and they analyzed them and said, but like only 10% of my samples were interesting because that was an anomaly. And if I'd only had a model that could have recognized that and better spent the time that I had there on that instrument to be able to do it, I'd be able to come up with much faster results, because now I have to wait 6 more months to get my turn on that machine. And that infrastructure of being able to discern between what's normal, where are there opportunities for innovation, and what's something that I should take notice of, I expect to become much more pervasive for us, but we'll see what happens with that. It's difficult.
All right. So now time for our lightning round. The 3 questions. So the 3 wishes. So Paul has let me become a genie, so I get to grant each of you 3 wishes. And genie rules apply. You can't ask for more wishes. And you also can't wish something for your products that you've designed. So, thinking outside the box, not limited to your role or your company. In 90 seconds each, we'll start with you, Al. What are your 3 wishes, if you had anything that you could wave a magic wand for?
If I had anything to wave a magic wand, and it's not to bring me a bucket full of cash and things like that. The first thing is I would like every hardware or process technology engineer to understand a lot more about software, and I'd like every software engineer to understand a lot more about the hardware and processes. I wish we had a lot more cross-disciplinary capabilities that used to be, I think, a lot more in the industry, and as we became specialized, they started to go separate, and I think it's time to bring that back. So that's actually my first wish, is in the engineering community. The second wish I would have is there a way to, for this whole question about legacy and how to fit into that, which really drives, the need for evolutions as opposed to revolutions. You're not going to make a leap forward without that, and so some way to go solve that. And I don't know what that answer is, because there's an economic reality to that.
It's a wand wave, so that would have solved it.
Yeah.
All right. And your last one?
The last one is probably go back to what I was saying earlier, is that I think there's a lot of work in various algorithms today, but no one, I think, understands where the fundamental is of just, what is an optimized algorithm? Am I at the equivalent of a Shannon limit? And if you understood that, then I think there could be, more fundamentals about how you approach the problem. You'd understand the workload, and therefore how to optimize the balance in the system between compute, memory, and communications better than we're probably doing today.
So we all need multiple PhDs, he's saying. Okay. So Paul, what are your 3 wishes?
I came up with this question and I never thought about my answer before just now. So I'm feeling what I'm hearing here, and I think number one, I'd like to see a lot more co-design between software and hardware, and more to it than that. I think from the APIs to the bits on the wire, we need to have much better and more disciplined, mathematically, formally provable, perhaps, relationships. So APIs to bits on the wire, that's a Shannon thing, basically. And another aspect of thinking about that is, instead of just having Shannon as a one-way channel, which it typically is described as, it's really a bidirectional synchronization, and we can do that on our modern networks. The second thing, that was the second thing. The third thing, I think, would be, I'd love to solve the power dissipation problem. It's dear to my heart. I was on one of the early experiments that measured the sea surface temperature at University College London. I actually did some of the testing when I was an apprentice there, designing satellites and stuff to go in space. And I became sensitized to global warming a long time ago, and it's actually the thing that I concern about the most. And I do think there's an opportunity, as we switch from the way we do linear and array kind of processing to graph processing, we actually can use applied graph theory to move things around and to have relationships that not only make the computation a lot faster and lower latency, but it also can do this, let me say, power or energy gerrymandering.
All right, great. Manoj, what are your 3 wishes?
Sure. I think maybe I'll start getting more tactical and maybe specific about what we look for, at least in the next, say, 5 years. I'm not going to go beyond that, maybe 5 to 7 years. One thing which I see that, I'm still stick the Al's point of picojoule per millimeter still sticking with me. I think we need to continue to see, we would love to see where the technology allows us to be much more efficient, especially will be in the area of more and more packaging together with the chiplets and etc. Because I think that this is where our Moore's law is leading. We are going to have a lot more things working on a system, on a wafer kind of so more technologies, more open technologies, collaboration, which basically brings me to the point of the openness aspect. But before that, I actually just want to talk about that. The second part is basically, as we going to start seeing this larger and larger components working together, it also comes to the Paul's point, but also power delivery. Power delivery is going to be a challenge. You're talking about racks basically having GPU, the whole rack basically, how much power we deliver, how much each component can be delivered, and of course how they can be cooled. So the cool important technologies are going to be in this space. So we look forward to that solutions. For all of this, I think it's going to be critical to have openness in the ecosystem getting better. I think we are getting more and more proprietary as we look into the system. So I don't know how, but definitely sharing of more data about use cases, which comes from people like us, but also for implementation choices, technologies that allow multiple chiplets and everybody to work together, networking technologies to work together from the problem perspective. I think these are the 3 things that is going to be important for us to deliver most efficient systems going 5 to 7 years from now.
Okay, great. CJ?
You asked us to think out of the box. So one of the things that I have really found compelling for me is to think with more of an abundance mentality rather than a scarcity mentality, and of looking rather than how can we sort of protect ourselves, self-assert ourselves, and sort of grab with what's best for ourselves, which tends to divide us and separate us, of looking at where can we build connections, where can we bring the most out of other people and have a greater sense of optimism. The second thing is an application of that. I think that there's an opportunity for us in this storage space for us to look at what the new requirements are for applications as that's being reflected in what we need for technology, including with storage. Had lots of discussions with storage vendors this week of looking at, for example, how we can get more fine-grained IOPS out of the media and the storage controllers. So specifically looking at how can we together discern, set up a framework where across a number of vendors and for the sake of the industry can discern what do we need and how do we best fulfill that and where maybe we need to push standards forward in that space. Just another very different thing that is a concern for me in this country and as a citizen here. If any of us thinks that any of our data is protected and secure, we have another thing coming. And the only way forward I think that we have for that is for us as technologists to work towards being able to achieve security by default. And that means that it needs to be low overhead. It needs to be the easiest thing to do instead of requiring additional extra special effort to make that happen. And I think that there's a lot of movement in that space for being able to advance that, but we have a long ways to go.
So I guess CJ's had the NSA visit. Okay. That's probably most of you had at one point. And Rita, I saved you for last.
Thank you. So in typical engineering fashion, I have a clarification about the requirement.
Okay. I've been on both sides of this argument. I was an engineer once upon a time, and I was product marketing manager, so I got to argue both sides.
You never said they have to be realistic, right?
Oh, no, they don't have to be
okay,
realistic.
Cool. Well, I mean, for purely selfish reasons, I would like to see AGI in my lifetime, right? Generalized intelligence. I think that would be cool. Yes, it is going to change the way we work and the way we think and the way we learn, but gosh darn it, it would be so cool to see it actually happen. The second one is kind of, have been mentioned a few times, and that is the concept of sustainability, right? We are making this globe warmer. We as a community are heavily contributing into that. We're consuming power. None of it is sustainable. None of it is recyclable. It is getting very, very scary. And the third one, I think the AI community and us as memory and storage, we are so focused on saving every bit of data, but at the same time, us as humans, one of our superpowers is the fact that we can forget things. And I don't think, especially with the FOMO right now, that we're even daring to poke at that big bubble. So it would be good to start to understand what it means to forget some data, because it is in the long term more sustainable.
Right.
That's how our brains work. And I think those are my 3.
All right, great. So I think we can open it up to questions now. All right, you were ready, man.
Yes, my name is David Schwader. I'd like to commend the gentleman from NVIDIA who said, if you think your data is safe, you better think again. The forthcoming quantum candidates coming out of NIST are not proven to be unbreakable. Therefore, they are not secure by design. According to Jen Easterly, we are all, ladies and gentlemen, crash dummies. Booth 646 combines quantum qubit superpositioning with, listen for it, Shannon perfect secrecy, which has been mentioned many times. If you want to improve the ROI of your products, help your customers protect their data with a data encryption technology that is not breakable by any method that is known other than brute force. And I'll be happy to talk to anybody, and I'd be happy to come to NVIDIA. I'll be happy to come to Intel, Solidigm, anywhere. You can all throw rocks at me. I'll be the only person left standing. If there's any questions, fire them at me.
Okay.